Section expected value. If x is a random variable, a discrete random variable with values x1, x2, and so on, and with corresponding probabilities p1, p2, and so on, then we defined the expected value of x that can be denoted by the symbol, the Greek letter mu with subscript x, and it's going to be equal to the sum of the multiplication of each value of x times its corresponding probability. Expected value of x. And beside that, beside the definition, if we have a function, if h is a function of the random variable x, then we can also compute the expected value of the function evaluated at x. And it's going to be it's almost the same as before. We have to do the sum, but apply the function h to each of the x values times the corresponding probability. And if I have a random variable determined by a times x plus b, where a and b are constants, then the expected value of y is a times the expected value of x plus b. From this result, the expected value of ax is equal to a times x, the expected value of x, and the expected value of a constant is only the constant. What is expected value? Expected value tries to be like an average. You know, we have several ways to compute averages for when we have several numbers. For example, I think the most common average we can compute is the numerical average. When you add all the numbers and divide by the total amount of numbers. When you do that, you are computing an average. That average is called the numerical average or the mean. But that is not the only way in which we can compute the average. Remember that an average tries to be like a representative number from all the numbers. Like we can say that intuitively that all the numbers are close or very close to the given number that we define as the average. And the most common way to do that is the numerical average. But other way to do that, when we have several values for a random variable, is by using the definition. Multiply each value of x times its probability, and then add all the values. And then we have all of these properties. For example, what is the expected value of b? If we have a random variable that always has the same value, b, always occurs the same value, b, what is the expected value of that? I mean, what is the expected value what is the value you expect to see? Obviously b, because actually the only value you can see. Oh well, of course, we will try to understand this by seeing examples. So let's see some examples. Example, consider the random variable x that counts the number of heads when tossing a fair coin 3 times. So the values for x here, you can verify if you compute the sample space and then obtain the corresponding value for x. The possible value for x they are 0, 1, 2, and 3. And the corresponding probabilities they are going to be 1 over 8, 3 over 8, 3 over 8, and 1 over 8. And remember that we call this the distribution of x. So, question. Find the expected value of x. I mean, when we toss a fair coin 3 times, what is the expected value? The value in the average is going to be computed by using the expected value. What is the value that in the average we expect to see? So we have to use the definition. By definition, the expected value of x is going to be computed as each value of x times its corresponding probability. So it's going to be 0 times 1 over 8 plus 1 times 3 over 8 plus 2 times 3 over 8 plus 3 times 1 over 8. And if we continue like this is going to be only 1 times 3 over 8 is only 3 over 8 plus 2 times 3 over 8 is 6 over 8 plus 3 times 1 over 8 is only 3 over 8. And this is 12 over 8. If we simplify, this is going to be divided by 2. We have 6 over 4. Divided by 2 again. is 3 over 2. Or in this context, we can use numbers, um, decimals, 1.5. What are we talking about here? We're talking about number of heads. So these values, they represent heads. So the average is heads, 1.5 heads. And maybe you wonder, wait a minute, can we see 1.5 heads? Of course not, right? I mean, we cannot take exact 1.5 heads, but this is, remember, this is only an average. It's trying to be like a representative for this. We can say that one way to think of this is that if we could repeat this experiment 10 times, tossing the coin 3 times, but we repeat that experiment 10 times, in the average, we can expect to see 1.5 times 10, 15 heads. That is one possible interpretation for that. So the average, the expected value when you toss a coin 3 times is 1.5 heads. So I'm going to write that. By repeating this experiment many times, we would expect to see in the long run an average of 1.5 heads. Yeah, I know it's weird, but remember, this is an average. It's trying to be like a representative number out of all of these numbers, 0, 1, 2, 3, when you toss a fair coin 3 times. All right. Next. In the same example, find the variance. Did I define the variance? No, I haven't defined that. Find the variance of x. The variance, denoted in this way, variance of x, is defined as the expected value of x minus its expected value raised to square. This is called variance. The variance is a measure of variability, measure of a spread of the numbers. How spread are the numbers in the average? That number, that answer can be responded by using the variance. So in this case, let's compute it. Compute the variance. Find the variance for this example. In our example, we have to compute this variance of x is equal to the expected value of x minus mu of x raised to the square. Or what is the same in our example, the expected value of x minus the expected value here was 1.5 heads. Yeah. So minus 1.5. So in other words, I have to subtract each value of x minus 1.5 and then raise to the squared, and then multiply that times the probability. Notice here, how can I compute this? Expected value of x minus a number raised to a power. In this case, I can take advantage of this formula, right? Because I have here, when you have the expected value, not only of x, but of a function in terms of x, represented by h of x. is only apply the function h to the x values and then times the corresponding probability. The h function in this case is going to be x minus the expected value raised to the square, or x minus 1.5 raised to the square. So here, h of x is equal to x minus 1.5 raised to the square. So that the variance of x is equal to the expected value of h of x. That in this case is going to be equal, according to the definition, apply apply h to each x value and multiply times the corresponding probability. So I have to subtract 0 minus 1.5 times the probability, 1 minus 1.5 times the probability, and so on. It's going to be 0 minus the mean or the expected value, that is 1.5, raised to the square times the probability, 1 over 8, plus 1 minus 1.5 raised to the square times the corresponding probability, that is 3 over 8, plus 2 minus 1.5 raised to the square times 3 over 8, plus 3 minus 1.5 raised to the square times 1 over 8. Each value minus the mean raised to the square times the probability. And if you compute this, you can verify that this sum is going to be equal to 0.75. So the variance of x is 0.75. Now, the variance is useful, but I think it's more useful the standard deviation. Standard deviation is equivalent to the variance. Standard deviation, denoted here by sigma x, is going to be equal to the positive square root of the variance. This is standard deviation. So in our example, the standard deviation is equal to square root of the variance, that is 0.75, and that is approximately 0.87. How can I interpret this? I can say that the variability among the values when tossing a coin 3 times is 0.87 heads in the average. Yeah, it's weird again because we don't have we're talking about heads and we don't have a natural number. But again, this is other average, but this average tries to measure the variability. We say that according to this in the average, we can expect that each value, the variability for each value with respect to the mean is approximately 0.87 heads, or more or less 1 head, right? All right. There is other way to compute the variance, a shortcut. Shortcut for variance. The variance, we could prove that the variance can be computed as the expected value of x squared minus the expected value of x raised to the square. It's not the same, yeah? Here, I'm trying to compute the expected value for the random variable raised to the square, and here is the value of the expected value raised to the square. For example, in our example, we know that the expected value is it's 1.5. So we need to compute the expected value of x squared. But by definition, again, we have to raise each value of x raised to the square times the probability and then add. It's going to be 1 squared times 1 over 8 plus, no, I'm sorry, 0 squared. 0 squared times 1 over 8 plus 1 squared times 3 over 8 plus 2 squared times 1 over 8 times 3 over 8 plus 3 squared times 1 over 8. And this is only 3 over 8 plus 12 over 8 plus 9 over 8. And this is only 24 over 8. That is only 3, right? So this is the expected value of x, and this is the expected value of x squared. Then the variance, other way to compute the variance should be this minus this. I mean, this value minus this value raised to the square. So will be 3 squared, no, 3 minus 1.5 raised to the square. And this is 3 minus 2.25, you can verify that. And this is only 0.75. Of course, the same value we obtained before. You see? All right. Now let's see some examples from web work. It says, this example is from web work. So first, to examine the effectiveness of its 4 annual advertising promotions, a mail order company has sent a questionnaire to each of its customers, asking how many of the previous year's promotions prompted orders that would not have otherwise been made. The accompanying table lists the probability that were derived from the questionnaire. Probabilities are these ones, you see? We see there a random variable x. If we assume that overall customer behavior next year will be the same as last year, what is the expected number of promotions that each customer will take advantage of next year by ordering goods that otherwise would not be purchased? So here, first we have to compute the expected value. Notice here, we have a table for values of x and the corresponding probabilities. So we don't know how to compute the expected value. The expected value, in this case, the expected value of x is going to be 0 times 0.63, no, 0.063, plus 1 times 0.21 plus 2 times 0.392 plus 3 times 0.19 plus 4 times 0.145. So what am I doing here? I'm computing the expected value for this random variable x based on the definition. Each value times its probability. Each value times its corresponding probability, and then add. If you can verify that this sum is going to be 2.144. I mean, the value we have here, right? This one. So let's say that this is the part A. Part B is the other question. This is part A. Oh my God. So now it says, I'm reading here. A previous analysis of historical records found that the mean value of orders for promotional goods is $37, with the company earning a gross profit of 24% on each order. Calculate the expected value of the profit contribution next year. So 37. So in this case, we have remember that X is representing the number of promotions that prompted orders. Number of promotions. So if we say it here that if we are being set here that the value of orders for promotional goods is 37 each, and we expect to have a 25% of profit. So in this case, we have to multiply the expected value of orders, that is 2.144, times the dollars, $37, times the profit they expect to make, that is 0.24, oh well, 24%. And if you multiply this, 2.144 times 37 times 0.24, you are supposed to get the value that you see in your screen. That is 19.03872. Finally, the part C. The part C, the fixed cost of conducting the 4 promotions. This is confusing. This is part A. This is part B. This is part C. The fixed cost of conducting the 4 promotions is estimated to be $10,000 with a variable cost of $3.75 per customer for mailing and handling costs. What is the minimum number of customers required by the company in order to cover the cost of promotions? So in this case, we have to find the break even point. So in this case, we have to make we have to set up it says the fixed cost of conducting the 4 promotions estimated to be $10,000 with a variable cost of 3.75 per customer. For mailing and handling costs, what is the minimum? So we have so let's understand this. This is 2.144 orders per client, right? The accompanying table lists the properties that were derived from the questionnaire where X represent the number of promotions that prompted order promotions, right? So we have each of these per client. So if X is the number of clients, then our profit is going to be determined by the expected value of 4 promotions, 2.144, times the number of clients, X. And from this is our, we can say this is going to be our revenue. No, wait a minute. No, I'm sorry. I was looking at the wrong numbers. From the part B, we already have the profit. The expected value of the profit contribution is this one. 19.03872 per client. So this is going to be wait a minute, why do they call I think this is not, I mean, well, they call this profit, but I think it should be called revenue instead of profit because we haven't subtracted the costs or, well, the point is that our total profit is going to be what we earn per client. So 19.030872 times X minus, we have to subtract the cost. The cost is 3.75 per client because it's variable, 3.75 X minus the fixed cost, 10,000. So you want to know the break-even point, and after that, we're going to be earning money. I mean, that's actually going to be the profit. Then we have to set this equal to 0 to know the break-even point. So if we factor here the X, this is going to be X times 19.03872 minus 3.75 minus 10,000 should be equal to 0. And here, solve for X. I will continue here with this problem. We have X times 19.03872 minus 3.75 minus 10,000 should be equal to 0. So we need to isolate the X. We can cancel this by adding 10,000 at both sides, 10,000, and then this implies X times 19.03872 minus 3.75 is equal to 10,000. And then divide by this at both sides, and we are going to have X is equal to 10,000 divided by 19.03872 minus 3.75. And that amount is going to be 655 approximately. You can verify that. It's going to be approximately 655 clients. Well, they say customer here, right? So customers. And this is the answer. All right. Next example, other from WebWork. For a random variable x, suppose the expected value of x is 4 and the variance is 8. Find this, the expected value of 2 plus x raised to the square. Here you have two options. You can, well, no, we can do it with the formula that we have seen, expected value of h of x, where here h of x is the function of x, that is 2 plus x raised to the square. Oh, no, we cannot use this here, because we don't have, we are given only the expected value. I mean, we don't have the, we don't have the, what are all the values for x? So yeah, I'm sorry. So we cannot do like that. Well, no problem. I'm sorry for this, no problem. So in this case, we have to do it by using more algebra. So this is the expected value. We have to develop this binomial. 2 plus x raised to the square is going to be, it's a binomial raised to the square, so it's 2 squared, that is 4, plus twice the product of 2 times x. So 2 times 2 is 4, 4x, plus x squared. You see? And then 4 plus 4x. By the way, one property of the expected value we can use when we have independent variables, or, well, I mean, in this case, don't worry about that. You can use the property that when you have the expected value of a sum, you can distribute the expected value in all the terms of the sum. I mean, this is going to be the same as the expected value of 4 plus the expected value of 4x plus the expected value of x squared. The expected value of a constant is only 4. I mean, the constant. Here we can use the property a constant times x. We can take advantage of this property that I mentioned at the beginning. When you have a constant times x, you can take out the constant, right? So it's going to be 4 times the expected value of x plus the expected value of x squared. And this is equal to 4 plus 4 times the expected value of x is 4, 4 times 4, plus the expected value of x squared. How are we going to compute the expected value of x squared if we don't have the values for x? I mean, all the positive values of the random variable x. Well, no problem. I'm going to do it here in the top. Remember that the variance of x is equal to the expected value of x squared minus the expected value of x raised to the square. So we solve for expected value of x squared. Here we're going to have expected value of x squared is equal to the variance of x plus the expected value of x raised to the square. So in our example, the variance of x is going to be the expected value, the variance, I'm sorry. the expected value of x squared is going to be equal to the variance that is 8 plus the expected value of x raised to square. The expected value of x is 4 raised to square is 16. So substitute this here. We're going to have 4 plus 16 plus 8 plus 16. That, as you can see, that is the answer that Webwork has, right? This one. 4 plus 16 plus 8 plus 16. I know this is going to be 16 plus 16 is 32 plus 8 is 44. But I don't know why Webwork has the answer like that. Yeah, I substituted the value for this from here. And I use this formula. The formula we saw before. Next one. Notice, how can we compute this one? Variance of 4 plus 3x. First, we will need a property for variance. The variance of a plus bx is equal to b squared times the variance. That property is true. I mean, when we have a plus bx, the variance, the constant a that is alone, it vanishes, and we have to raise b2 squared and then times the variance. So in our problem, we have variance of 4 plus 3x. We ignore the 4, so we have only 3 squared times the variance. And it's going to be 9 times the variance, that is 8. And notice, this is the answer Webwork has. See? One more example. It says, suppose that a pair of dice is tossed. One die has 7 sides, the other has 6 sides. What is the expected value of the sum of the two dice? First, let x be the number in the first die, and let y be the number in the second die. If we assume that the die the first one has 6 sides, I mean, it says one has 7 sides and the other has 6 sides. So let's say that x has 7 sides and the y has 6 sides. So if it is a fair die, then the values for x, they are going to be like this, right? 1, 2, 3, 4, 5, 6, and 7. And each is going to have a probability of 1/7 to occur. 1/7, 1/7, 1/7, 1/7, 1/7, 1/7, and 1/7. Since we have 7 numbers, and we are assuming that it's a fair die, then each number should have 1/7 of probability to occur. So the expected value of x should be the sum 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 divided by 7. It's only the numerical average, right, in this case. So this is going to be, the sum here is 28 divided by 7, and this is equal to 4. The expected value for x is equal to 4. You can verify that the expected value for y is going to be 3.5 with the same reasoning. To get the value for y, to get the expected value for y, create a table with the y values. In this case, they're going to be 1, 2, 3, 4, 5, 6. Oh, well, actually, I mean, in the example, we computed before, right? No, I'm sorry. We didn't compute for a die. We computed for tossing a coin 3 times. Oh, well. How you can verify this number? Create a table for the y values. If it has 6 sides, it's going to be 1, 2, 3, 4, 5, up to 6. With the cards, if the die is fair, then will be the probabilities 1 over 6, 1 over 6, 1 over 6. So add the numbers up to 6 and divide by 6. The number you should have is 3.5. But the question is not this. The question is, what is the expected value of the sum of x plus y? And in this case, fortunately, you can take advantage of this formula. The expected value of x plus y is only the expected value of x plus the expected value of y. So in this case, it's going to be only 4 plus 3.5. That is only 7.5. That is the answer we have here, right? All right, one more example. Last one. Other from WebWork. A game of chance involves rolling an unevenly balanced four-sided die. Four-sided die. The probability that the roll comes up 1 is 0.15. So I'm going to denote this by probability of 1 is 0.15. The probability that a roll comes up 1 or 2 is 0.43. The probability that comes up 2 or 3 is 0.47. And it says, if you win the amount that appears on the die, what is your expected winnings? Know that the die has 4 sides. So in this case, to compute the expected value, we need to have, of course, the values for x with the corresponding probabilities. I'm going to write it here. So we have the x values and the probabilities. But we know that here in this case, 1, we know for sure this has probability 0.15. But we need to figure out the probabilities for the other values. But how? We don't have exactly in this case, notice the probability for 2. It's probability of 1 or 2. Well, in this case, probability of 2 is going to be the probability of 1 or 2 minus the probability of 1. I mean, if we know that that 1 or 2 can occur, I mean, there's no possible way that we can consider the intersection of that. I mean, how can we have this context we observe 1 and 2 at the same time. No, so this means that 1 or 2 means the probability of 1 and the probability of 2 added. So we want to compute the probability for 2 only. Subtract from probability of 1 or 2, probability of 1. In this case, it's going to be 0.43 minus 0.15. That is 0.28. So this goes here, 0.28. The same reasoning for the probability of 3 is probability of 2 or 3 minus the probability of 2. That is going to be 0.47 minus 0.28. Then in this case, it's going to be 0.19. So this goes here. Now, how do we know the probability of 4? Well, remember that the distribution for any random variable x must be 1 when you add it, when you add all the values, right? So how can we know the value that goes here? Very simple. Add these values and subtract from 1. If you do it, you will realize that the value that is missing here is 0.38. Yeah? Again, I'm sorry. How do you get the values? The value that goes here? Add these values, subtract from 1. The answer is going to be 0.38. Now you have the x values and the corresponding probabilities. How do you compute the expected value? Well, remember the expected value of x is equal to each value times its probability. If you do it correctly, you can verify that the answer is going to be actually 2.8, the one we have here. All right, that's all by now. See you in the next video.